Our lesson for today is all about proving inequalities in triangle. Triangle inequality tells that for any triangle, the sum of the lengths of any two sides is greater than the length of the third side. The theorems on triangle are given. Let's discuss first the inequalities in one triangle. We have triangle inequality theorem 1. If one side of a triangle is longer than a second side, then the angle opposite the first side is larger than the angle opposite the second side. Looking at triangle FIN on the slide, triangle FIN has three sides, namely line segment FI, line segment FN, and line segment IN, and three angles are angle F, angle I, and angle N. The opposite angle of line segment FI is angle N, and the angle opposite to line segment FN is angle I, while the opposite angle of line segment IN is angle F. Now, if line segment IN is equal to 10 and line segment FI is equal to 9, then we can say that line segment IN is greater than line segment FI, since the angle opposite to side line segment IN is angle F, and the angle opposite to side line segment FI is angle N. We conclude that angle F is greater than angle N. Now, using a two-column proof, we can prove inequalities in a triangle by applying these theorems, such as: given the triangle SET is an isosceles. We all know that when we say isosceles triangle, it has two congruent sides. Line segment ST is greater than line segment SE, and line segment ST is equal to 15, while line segment SE is equal to 11. Let's prove the degree measure of angle SET is greater than the degree measure of angle STE. So, for our first statement, we have line segment ST is equal to 15 and line segment SE is equal to 11. Our reason here is given. And for our second statement, line segment ST is greater than line segment SE. The reason is also given. For our third statement, line segment SE is congruent to line segment SE. The reason? By the definition of isosceles triangle. And for our last statement, the degree measure of angle SET is greater than the degree measure of angle STE. And the reason is by the property of inequality. Now, let's proceed to the triangle inequality theorem 2. If one angle of a triangle is larger than a second angle, then the side opposite the first angle is longer than the side opposite the second angle. Moving on with the second theorem of triangle inequality, given triangle ABC, the degree measure of angle A is equal to 60 degrees. The degree measure of angle B is equal to 30 degrees, and the degree measure of angle C is equal to 90 degrees. We can say that the side opposite angle A is greater than the side opposite of angle B. In this example, the opposite side of angle A is side BC or line segment BC, while angle B, its opposite side is line segment AC. Since the degree measure of angle A is greater than the degree measure of angle B, therefore, BC or line segment BC is greater than AC or line segment AC. That is the triangle inequality theorem 2. Next, for our triangle inequality theorem 3, the sum of the lengths of any two sides of a triangle is greater than the length of the third side. In this triangle inequality, you will add the lengths of any two sides. The sum of the two sides should be greater than the third side or the third side. For example, let's construct triangle TAG with the measure of lengths. TA is equal to 12, AG is equal to 15, and TG is equal to 26. Now, if TA or the measure of TA plus the measure of AG is equal to 27, and TA plus or the measure of TA plus the measure of TG is equal to 38, the measure of TG plus the measure of AG is equal to 41, then TA plus AG is greater than TG or the measure of TG. TA plus TG is greater than the measure of line segment AG, and TG plus AG is greater than the line segment of TA. Another given triangle ABC, the following relationship can be drawn. Line segment AB plus line segment BC is greater than line segment AC. Line segment BC plus line segment AC is greater than line segment AB. And line segment AB plus line segment AC is greater than line segment BC. Now, based on the measures of the three sides, can 6, 14, and 4 can be sides of a triangle? Now, for our solution, using the triangle inequality theorem, let's add. So we have line segment AB plus line segment BC is greater than line segment AC. So from here, we just substitute the value. So for the value of our line segment AB, that is 4, while the value of line segment or the measure of line segment BC is 14, and the measure of line segment AC is 6. Next, line segment BC plus line segment AC is greater than line segment AB. Again, let's substitute the measure of the following sides. The measure of line segment BC is 14 plus the measure of line segment AC is 6 and greater than line segment AB, which is 4. And for our last, line segment AB plus line segment AC is greater than the measure of line segment BC. For if we substitute the value, the measure of line segment AB is 4, the measure of line segment AC is 6, and the measure of line segment BC is 14. Now, based on the example, since 4 plus 6 is not greater than 14, therefore 6, 14, and 4 cannot be the sides of a triangle. That is the triangle inequality theorem all about. Next, let's proceed to the exterior angle inequality theorem. The measure of an exterior angle of a triangle is greater than the measure of either remote interior angle. Given the triangle DAM, line segment MA extends to point P. The degree measure of angle M is 50, and the degree measure of angle DAP is equal to 110 degrees. Referring to the illustration on the slide, angle DAP is an exterior angle. Angle M and angle D are the remote interior angles. Through the exterior inequality theorem, we can say that the degree measure of angle DAP is greater than the degree measure of angle DMA, and the degree measure of angle DAP is greater than the degree measure of angle MDA. Now, the following theorems are hinge theorem and converse of hinge theorem, which are used to prove inequalities in two triangles. Let's have an example using the two-column proof. Given the figure below, or given the figure on the slide, let us prove that the degree measure of angle BCE is greater than the degree measure of angle DBA. So again, for our proof, for our first statement, the degree measure of angle BCE is greater than the degree measure of angle CDB. The reason? Based on the definition of exterior angle inequality theorem. Next statement, the degree measure of angle CDB is greater than the degree measure of angle DBA, and the reason is based on the definition of exterior angle inequality theorem 2. And next, for our last statement, the degree measure of angle BCE is greater than the degree measure of angle DBA, and for our reason, based on the transitive property of inequality. Now, after we discuss the inequalities in one triangle, let's proceed now to the inequalities in two triangles. So we have the hinge theorem. If two sides of one triangle are congruent to two sides of another triangle, but the included angle of the first triangle is greater than the included angle of the second, then the third side of the first triangle is longer than the third side of the second. Given the triangle BOD and triangle TIP, the degree measure of angle O is 49 degrees, and the degree measure of angle of angle I is 40 degrees. Note this, that the triangle BOD and the triangle TIP, that line segment BO is congruent to line segment TI, and line segment OD is congruent to line segment IP. In triangle BOD, angle O is the included angle of sides BO and OD, while in triangle TIP, angle I is the included angle of sides line segment TI and line segment IP. Since angle O is equal to 49 degrees, while the angle I is equal to 40 degrees, then line segment BD is greater than line segment TP. Now, for our example, in triangle CBS and triangle JAF, line segment CB is congruent to line segment JA. Next, line segment CS is congruent to line segment JF, and the degree measure of angle C is less than to the degree measure of angle J. Use hinge theorem to give the conclusion. And for our solution, by hinge theorem, line segment BS is less than to line segment AF. That is the hinge theorem. Now, let's proceed to the converse of hinge theorem. If two sides of one triangle are congruent to two sides of another triangle, but the third side of the first triangle is longer than the third side of the second, then the included angle of the first triangle is larger than the included angle of the second. Now, in triangle FON and triangle PAL, line segment FO is congruent to line segment PA. Line segment ON is congruent to line segment AL. And line segment FN is less than to the measure of line segment PL. Then, we can say that angle A is greater than angle O. By constructing the constructed given triangles. Now, for example, consider triangle CBS and triangle JAF. Use the converse or the converse of the hinge theorem to give the conclusion. For our solution, since line segment CB is equal to the line segment JA and line segment CS is equal to line segment JF and line segment BS is equal to 24, therefore, angle C is greater than angle J by the converse of the hinge theorem. Now, let's have an example using the two-column proof. Given the triangle ACB, line segment AC is congruent to line segment BC. Line segment AR is less than to line segment BR. Let's prove the degree measure of angle ACR is less than to the degree measure of angle BCR. So again, we need our proof. So for our first statement, AC is congruent to BC or line segment BC. The reason is given. For our second statement, line segment CR is congruent to line segment CR. The reason? By reflexive property. For our third statement, line segment AR is less than to line segment BR. The reason is given. For our fourth statement, angle ACR and angle BCR are included angles. The reason? Based on the definition of included angle. And for our last statement, the degree measure of angle ACR is less than to the degree measure of angle BCR. And the reason here is by the definition of converse hinge theorem. I hope class you understand our lesson for today, which is proving inequalities in triangle. Thank you for watching.